OT world for the last 25 plus years, doing pretty much everything from SCADA up to IoT, cloud connections, and through all the mess, OEE, data handling, historians, reporting. So that's what I've been doing. So I've been doing a little bit of everything here. My role now is I'm a solution architect, business developer for new technology within Novatech, and I work closely with Veronica, of course. So welcome once more to this training. A little bit first about Novatech. We have been around since 1986, and what we have done is delivering solutions in the industrial automation space, digitalize different types of demands at customers across all segments and industries. We are approximately 150 employees and have around 300 million turnover. We have offices in Scandinavia, Switzerland, Holland, Belgium, and the UK, Ireland. We have more than 120 active implementation partners. And innovation is core. So we also started from the beginning. We started to innovate by using PC in the industrial space. So with that said, we go over to the agenda. This is a training. It will cover different topics. So it will be perhaps not so deep training. It's an overview training. So we will talk a little bit about basic cloud data terminology. What types of data sources would you have to send to deliver data to the cloud? Discuss a little bit what MQTT is as a protocol, so that normally used sending data here. Also the role of OPC UA, that's the industry standard. We will introduce the concept of industrial data ops, basically how you work in a structured way with your data so that it becomes easier to use, easier to handle. We will both discuss and demonstrate something called a unified namespace. And that's some terminology and a solution that comes now and is aimed for scaling the data handling at customer sites. And also touch base a little bit about the security aspects on this. So that's the agenda. So hopefully you find it interesting, and we'll get started. First of all, wanted to define what we mean with digital waste. So it's a terminology, but basically is data. I've written here, since the training is about sending OT data to the cloud. That's why I have it, but it's valid also for on-prem solutions. So data that is not used or monitored, that will, of course, introduce waste in creating, transmitting, and storing. It could be software costs, transmitting costs, but also labor costs. And if you're not using the data or monitor the quality of it, it will generate bad quality data. And that's definitely a waste. Data that's impossible to correlate. So if you have data that is very hard or impossible to correlate to what machine was it, what product was run on the machine at the time, etc., that is definitely missed opportunities. And because it's unable to find the whole picture. And we also see a little bit about cloud solutions where you actually model and contextualize data in the cloud. And we see that that might be both incomplete but also time consuming, because the people running the cloud architecture might not be the local OT people that actually knows the production site. So we'll lose long-term data quality because the production site is rebuilding, and if the cloud model is not up to date, we will have bad data. And of course, if you model it on a high level, it's hard to reuse on the edge or on-prem. And that is something we will see later on. The challenges we see here now when coming to Industry 4.0 is far more complex because of the system interaction. But the current approach that we see is that it has a system by system approach. Modeling is done in each application, trying to understand the data, try to contextualize it. Often custom integration code to collect and prepare the data, and sometimes, not always, developed and maintained by IT team. That's not a bad thing, but we need to get more correlation as we see it with the OT people, so that the OT people knows the machinery, the tags, the PLCs, and all that inside out. And they should be part of this. So what we do get then is that the system are not scaling. The IT system that relies on OT data are not scaling as they could. It takes time to integrate, and with that, the technical debt is increasing because you get redundant modeling, you get different types of modeling in different applications. And also the infrastructure is not resilient because you get a lot of integration points. The monitoring and security of those integration points might not be up to date because it's perhaps driven by a certain use case, a certain person, and so on. And this means that the data is not good quality, and that will induce that the analytics that you try to do with it, either it's visualization analytics or machine learning, is not trusted, and you don't get the scaling and business improvement that you aim for. So with that said, one day the OT person gets a call, and we have seen that many times. There are an initiative at the customer side, perhaps driven by IT, perhaps driven by a special data science team. They need production and process data in the enterprise cloud. Can you help us? That is the first touch point there. And of course, the OT people knows a little bit more about the OT data. So we'll take a little bit, but perhaps not that familiar. So we'll take a very, very brief overview of cloud terminology in the beginning here. We need to understand what is, on an overview perspective, of course, what is a data lake, the IoT connectors that you need to stream the data to the cloud, what is AI, machine learning analytics, and what is MQTT. That's some basics. A data lake, what is that? But that's basically a repository for big data and also for the analytics workloads around that. Hyperscale, it is on steroids in that sense. But it's basically a distributed file system for data of any type. It could be unstructured, semi-structured, or structured data. And of course, when you talk about sensor data, that is the OT's main type of data. That is that's unstructured, then it's not good. If it's semi-structured, that's better, but best would be if it's totally structured, of course. But if you just stream tag data straight up, then it basically becomes unstructured. But a data lake itself is not just about the storage itself, it's about getting data in, getting data out, handling and manipulating, catalogization, indexing, and visualization services. Otherwise, it's not useful. Otherwise, it's just a big black box. To get data in, you normally have some sort of IoT connector. That's the real-time gateway between the edge devices. That's the on-prem connectors that you have on the factory, and the cloud backend systems, the cloud services. It handles device to cloud communication. That's normally when we send sensor updates or machine updates. But it also handles cloud to device communication, because to be able to build a good solution, you must be able to take the information and knowledge from the cloud services back to the OT systems. But it can also be called remote method services, so that you can actually interact with the on-prem solutions. For certain applications, it also handles device management. If you have a huge amount of devices that you need to update BIOS or firmware or things like that. Normally you have protocols here, the MQTT, HTTP, or AMQP, that's a special for Azure. So basic terminology here is Azure IoT Hub, AWS IoT Core, and Google IoT Core. Those are the services, the endpoints where data is pushed to. And it also handles, of course, all the security between the on-prem device and the cloud. So that's a vital role for those. If you talk about analytics and machine learning, I normally say that I think this is a good picture of it, because it handles the different steps of analytics, the different types of analytics, and also sort of the journey going from top to bottom. So I will take a little bit about this. The first term is descriptive, what happened. That's basically a form of analytics also, where you actually out of that take decision and actions. That's normally what we say in the OT. That's alarms, quality defects. It's normally some sort of a KPI dashboarding, could be an alert, alarm list, or anything similar. It could also be somewhat historical values, what happened yesterday, what happened the last 7 days. But then when we have seen that something has happened, we need to do the root cause analysis. That's the diagnostics part. Still quite manual, not automated, but there are of course tools to help us do that. We use reports, we use trends, we use business intelligence tools to do slice and dice of the data, but also when you talked about statistical modeling, data-driven modeling, putting in historical data, try to model the defect, the problem, or emissions, or anything similar like that. But that comes in the next stage when you go into predictive. That's what you normally mean when you say analytics, machine learning. But I say that also the other two steps are the beginning of the analytics journey. Predictive, then you start to try to do different types of model. It could be neural networks or different types of statistical models, where you actually use historical data at time X to try to model some sort of KPI at time X plus 1 hour, plus 2 hours, plus 1 week, and so on, to predict the health, the failures, or just virtual sensors. And if you can find a good model fit for that, let's say 85% or 90% accuracy of that, then you have a pretty good prediction on what will happen if you continue to run like this. You will have a problem in 1 week or 1 hour or whatever time horizon you have. So now we have some sort of a prediction what will happen, but then we come to the last step. That's the sort of closed loop handling, where you actually do the prescriptive handling. Try to make a decision support system suggest what should the operator do, what should the technician do. But there's also be suggestion on set points to actually, and in the last step, actually control the production. And we see that at customer sites, where the edge is basically just the safety system. What should the process do if it loses the connection to the cloud? But otherwise, the edge is basically input-output. So the actual logic, the actual control is done via cloud services. So it's moving in that direction. Of course, for really fast application, that is still not a problem. It's still not a solution of today, but it will move more and more towards that. So if you take all these objects and try to put it a bit together. So basically what you have, we have the data lake that where we want to publish our data. We have the connector where we can get real-time data. Sorry, I will just take away I have to go over here. So get a small, when someone comes in, I get a small pop-up in the bottom here. So basically we have some legacy equipment with some legacy protocol. We need some sort of protocol converter. Most of you that is part of this call will probably know Kepware. That's what we normally use to convert the legacy protocol to OPC UA. Modern equipment will of course have OPC UA directly. And the traditional way is to have some sort of MQTT gateway, publish data to the cloud. If you have MQTT enabled equipment, it could publish directly. But then you have all the other types of data, the time series databases like historians, MES system, ERP, could be quality management systems, or other types of transactional or record-based solutions. You would normally have ETL, ELT pipelines like extract, transform, load, or extract, load, transform pipelines. If you talk about Azure, for example, that's Azure Data Factory normally. That actually pushes things from the locals to the data lake. And then you use that to visualize or do machine learning AI solutions. But if you visualize, you normally have like business intelligence tools. They could be in cloud, but they can be local also, of course. But if they are in cloud, you normally have some sort of direct query gateway. So if the data doesn't have to go to the data lake, you can actually query the local data directly. So that's just a bit of an overview on that. When we talk about MQTT, some of you are probably familiar with MQTT, but would take it as a background for this because it's quite vital when you talk about this type of solutions. The MQTT is a standard. It's an ISO standard to handle IoT data. So it has been around for quite some time. It's a broker-based communication. So you have a broker in the middle, and then all the clients use a pub-sub architecture, publish, subscribe. So basically you publish, if a temperature sensor gets a new value, it publish it to a certain topic. That's basically, normally when we talk about OT, that's an ISA 95 hierarchy. You publish it under the right object, the motor, the valve, etc. And then the broker gets it. The mobile device subscribe to the topic temperature. And when you get an update, it gets a publish back, a callback to the client with the new value of the temperature. So it's totally event driven, and that means that it's very bandwidth efficient also. It scales very well. So, but of course, the MQTT broker that you have could be built into the machine, it could be on the line, it could be on the plant level, but then you normally have some sort of a back-end system. And then you use basically an MQTT bridge or just federate. The changes here are federated to the enterprise-wide solution. I actually saw just a couple of days ago where you actually had a LoRaWAN gateway that had both the local MQTT broker into the gateway, in the physical gateway, but also the MQTT bridge to actually publish the data further up the stream. So now we know a little bit more. It's of course an overview, but we know a little bit more. So we're ready to take the discussion about the data that is going to the cloud. So we can understand, try to see what is the use case. Will it be real-time data to use with machine learning algorithms, or is it aggregated data like energy data, stops on the machine, downtime events, and things like that? And what data sources do we need to support that? Do we just need real-time data sources, or will it be also MES system involved, the EAM system, the asset management system? So we need to define that. How should the data be formatted? What is the expectation there? And what is the future vision of this initiative? And the future vision, I will come back to that later on, why it's important to actually know the vision so that we can architect a solution that will scale in the future. So I will answer that later on and come back to that later on in the presentation. So when we talk about MQTT and the real-time data, you will face another term here, and that's the payload. So MQTT is a transport protocol, but then you have the data part of the MQTT message. That's normally referred to as a payload. That's a discrete set of information that normally is correlated in time event. So most often it's something called JSON encoded. I will show the format for that. But if it's not correlated and time/event synchronized with context, it is a source of digital waste. So I will show a typical example of a simple MQTT gateway. When it publishes, this is an MQTT message that you see right now. Just 2 seconds, I will take the full screen here, where you basically have a timestamp. This is a Unix timestamp. So, and the values, you have just a tag name, value, quality, and timestamp for this sample. And then you have a new one, and that could be a huge list. It don't have any correlation. In this case, we can actually see that the tag name, this seems to be an RPM of a device one. This seems to be a flow. Fine. But this is a naming standard that you never know how many naming standards one site has. I would argue at least 10, probably closer to 30, 40. Even if you are working quite extensively with this, you get new machinery, you get different types of the production, the energy producing, the paper machine, the packaging machines, all those have different naming standards. And this becomes a problem when you publish data this way. So this is basically a JSON message that's part of the MQTT message. So this is the data that we do get to the data consumers. But that's when we start to talk about data ops. So what we try to do then is to standardize, normalize, and contextualize the data at the edge. So as soon as possible, we get it in, we try to make the data so that it actually can be used much easier in all the consuming applications. To do that, we need to connect to industrial and IT systems to combine the data, manage the flow of information, and provide the scale and security for industrial usage. So basically have connectors to all different types of systems to both read and write from those systems through standardized models. So if it is a pump of a certain type, could be a small pump, a large pump, could be a frequency controlled pump or an on and off pump, they have a unified model throughout the enterprise. And this gives us a huge benefit when we try to consume the data, of course. More on that later on. And it will have flows to control the data. How often? Should it be event-driven? Should it be on time? And then to be able to integrate all these types of systems, but also in a high frequency, so you can actually scale for tens of thousands of flows every second. So what we do get there, this is a bit technical, of course, but we had the timestamp for a simple MQTT gateway, the payload for the simple MQTT gateway. But what we try to achieve here, and this is just for your understanding, we try to put data in context. We try to normalize the data in what we call a data ops gateway. This means that instead of sending just raw tags, we actually say that we have an ID of the object, we have a model, which model is it built on, a timestamp, and on that timestamp, we did have a value for the RPM, and perhaps we should take flow instead, because there we can see the unit of measures, cubic meters per hour. It's not liters per second, it's cubic meters per hour. And of course, if we're talking about large enterprise scaling, it might be that certain factories is using imperial measures instead of metric measures. So then you need to convert so that the central location, the cloud, always have normalized data so that you can compare it. Status, if the motor is running or not. But here is also an important part, is basically saying that this object resides here in the ISO 95 standard. It's under the enterprise cleaning division, site ID Malmö, the area ID North, pump station 001, and it's pump 1 in that pump station. So then we have a reference, so we know enterprise-wide, we have a unique identifier for this. And that is something very, very important when you try to combine the data, because otherwise you will have controller 12. You will have that in 50 different locations. So you need to put it in the complete ISO 95 structure. And having this type of structure means that the apps that you build, they can work on the generic model. And then you can instantiate that model for 10 different pumps, for 100 different pumps, for 500 different pumps, and the app will still work because it's built on the model, not the instance or any other special handling. It will scale without a lot of manual work. We have different types of data sources when it comes to OT. We have real-time sensor data. That's what we have been talking quite a lot about here. That's used for root cause analysis. It's used for analytics machine learning, typically sensor data, normally connected via OPC UA or a protocol converter that takes the legacy protocol to OPC UA. But it could also be REST if you're using IoT sensors, for example. Aggregated data, that's basically things that is aggregated. You have 1 hour energy values, you have 1 day energy values, you have produced amount per production order. So you aggregate sensor data into actual records, basically. So energy data, running times, sort of historical data. We normally integrate that with SQL and REST or REST, because you do SQL queries or REST queries towards those type of data sources. Event data is more like alerts, downtime events, batch records. That's normally resides in some sort of SQL database on the local OT system. But we need to integrate to that also. And then we have those that is a little bit harder normally. That's basically if you have file type of data, like log files, quality tests, images. We normally integrate that via CSV, Parquet file format, or similar. But those are always a little bit harder because they don't standardize as well as the other ones. So I've been talking now about MQTT and claim that that is vital in Industry 4.0 to be able to scale. And then we always have an argument of what about OPC UA? That should be the standard for Industry 4.0. And I would say that it is. They will in my opinion, they will coexist because that is, OPC UA is very important in local machine communication because it's widely adopted but by all the suppliers in the OT space. It has the data access, it has events, but it also has methods, and that's important when you want to call a remote method in a printer saying clear your printer queue, for example. That is something that MQTT, for example, today does not have. It is an IEC standard. So but it has some limitations when it comes to scaling. It's quite network heavy. It's still quite polling. It has no generic modeling. It has modeling, but the modeling in OPC UA tend to be very focused on controls modeling. It comes from the OT space. It is focused on the more micro level than the macro level. Of course, you can build very advanced modeling in OPC also. And you have new technology with OPC UA called PubSub that can actually run over MQTT, but it's not that adopted as it is as of today. So I would argue that they will coexist. OPC UA will definitely be the source for a lot of the MQTT data, and it will be for local communication also. So now we come in a little bit on talking about unified namespace. Like I said, MQTT was invented to serve multiple data consumers and multiple data producers. And that means that for digital transformation, data in some way must be decoupled and provided over an enterprise-wide architecture. And that's where we talk about the unified namespace. The unified namespace is a structure where business and industrial data can be exchanged between, if we talk about departments, IT, OT. So basically, the UNS holds the current value of everything that is interesting in this space. It will normally not contain so much historical data, but it might be that it consists of some historical data sets that many clients find interesting. So basically, all these types of systems interact with the unified namespace, gets updates. For example, a SCADA system can get updates via the UNS, but also publish back alarms. The historian can get data via the UNS, but publish back some advanced emission calculation values that then can be consumed by other nodes in the ecosystem. So I will show a little bit in the demo around this. What does it look like? Normally it's based on MQTT, and you have a broker where you have something called a topic namespace. So basically that's a folder structure. So you publish data on, in this case, enterprise, site, area, line, work center, cell, work unit. This is an IMM, injection molding machine, that has some status, the current cycle time, the temperature, the status of the machine. But it can also, under SCADA topic, contain the current alarm list, X number of rows. It could be the top 10 orders to produce in the near future. It could be data about the current OEE for the current order or the current shift, whatever is interesting for the clients to consume. It could contain maintenance data, the time where we had last major service, last operator service. So that is the unified namespace. So if you take this a little, sorry, I forgot that I had it a bit more larger so that you can read it better. So basically all the raw data is there for the current information, but also a bit more information that is evaluated. The raw data, the sensor data is evaluated to an alarm list. So that is also published to the unified namespace. So all clients that is interested in the alarm list for this injection molding machine just subscribes to that topic. So whenever it gets an update, they will get a callback within milliseconds or perhaps a second or so to update their alarm list in the visualization or analytics. So with that, I will go over and take a very quick demo on how that can look in real time. So I will just let me share my virtual machine instead. So I will just give me 2 seconds and can you see my machine? Do you see it, Veronica? You are the one that can.
Yes, I see the blue screen. Yes, yes.
Yes, perfect. So this is a short demo of a data ops gateway that is called HiByte Intelligence Hub. So I will take a very quick overview of that. So basically what we have is that we have Kepware in the beginning where we have some simulated devices. We have device 1, device 2, device 3. Some simple pump where we have flow, RPM, status. So this is simulated data. So if you look into this, we can see here we have device 1, we have simulated data here coming in continuously. And then we go over to the configuration of the HiByte Intelligence Hub, where we're going to model this data and publish it. This is a web application. You just log in, you have connection, modeling, and flows, and some administrative things. You have connections. In this case, we have the local host Kepware. We have inputs here. Here we see all the inputs that we can use in our modeling. We can, of course, browse here and see, add more information into the modeling tool. We can also define outputs if we want to write values back to Kepware, aka PLCs, etc. With that, we have an output here also for an MQTT broker. So we have an MQTT broker here where we have outputs defined. So for example, we have an ISA 95 enterprise output. Under this topic, we publish everything that should go on the enterprise level of the ISA 95 standard and etc. But all these topics are dynamically built out of the configuration of the object. So if you configure an area that's called north, as you can see area here, the area ID is part of the topic namespace, as you can see here. So that means if you say area north, we will publish it under north. If it's south, we will publish it under south. You will see that live in a minute. But we also have a connection to Azure in this case. So we have an Azure connection where we actually connect to Azure to an IoT hub and send data. In this case, we're sending it over HTTPS, but it could be MQTT also. So if we go over to modeling, we have some different types of modeling. In this case, we have the pump advanced model. It's not so very advanced. it actually only has an RPM, a flow, a status, the ISA 95 reference, and that's some legacy. It shouldn't be there, but it's a legacy information. With this, we can see where we have who is using this model. In this case, we can go in and see Malmö North Pump Station 001 Pump 1 is using this. How is it using it? It's basically saying that the RPM is a model in a model. So that's basically a more advanced object that reads the RPM from Kepware. We can just take input and say Kepware, and we can just drag and drop and say this one goes here. We have a hard-coded unit of measure. It has a low and high EGU. And that's vital information for a data scientist or anybody that is going to work on this data to know what type of data it is, what measurement range do we have. That helps a lot when you do. And I've been doing a lot of reporting, for example. Then it's very vital to know, is it kilowatts or kilowatt hours? That's normally not unified in the SCADA or historians. Unfortunately not. So now we have modeled the instance, and we then have flows. In this case, we are going to publish it under the UNS 1, 2, 3, 5, 6. That's the levels of my just interpretation of the levels. That's just a name. You can have any name you want. So under the status topic, these are the objects to be published there. And if you look into this, we see that it's pump station 1, pump 1, and pump 2 that is sent out to this topic. In this case, enterprise site area work unit equipment module status topic. It's sent every 10 seconds. And if we look into it, how does that look? This is the MQTT Explorer looking at this MQTT broker. So now we have cleaning division, Malmö North Pump Station 1, Pump 1 status. This is the message that is sent every 10 seconds. There is a message sent to this topic. And this is the structure that we saw in the presentation earlier on. So whoever is interested in this will get updates. As soon as this is published, they will get an update, and they can do recording, they can do alarming, they can do machine learning, anything with this information. And then we publish some CMMS data. In this case, we have top 5 service requests. This one is due in 10 days, and this one is due in 2 days. In 2 days, we are going to do a lubrication service. And here we can have different topics for different types of information.
I have here the flow that published to the UNS to the pump station data for the pumps. I have here pump 1 and pump 2 for pump station 1. And I will now add the instance, and I will add a pump station 12, pump 1, to the same flow. So it will publish on the same UNS, but since the path and topic path is dynamic, built out of the ISA 95 configuration, it will publish this pump under south instead. So as soon as I press save and go over to the UNS, I suddenly get the pump station 12 pump 1. And here I have the message for that pump.
Can you see my screen, my presentation now, Veronica?
Yes, absolutely.
And of course, the challenging part. This will be a very brief overview, but security. That's always a topic when you start to connect local on-prem solutions with cloud solutions. First of all, do your risk assessment. basically, what if cloud connectivity is gone? Can we run our business? Map the cloud dependencies to OT functionality. That's basically a very, very important thing to do. And when you know the dependencies, you can do risk assessment to say, what would that mean to us if this fails? Create security visibility on cloud deployments. So basically build your dashboards to see how many consumers do you have, how much do you consume, who is logging in, logging out, failed login, all these things. You need to get the visibility on that so that you have a cockpit or dashboard for that, so that you find anomalies as soon as they occur. And of course, define the KPIs. What do you want to have out of it? Review the service level agreement with cloud service provider. So if you integrate a service provider that guarantees, what are their guarantees? How can we use their functionality to secure our local risk handling? And investigate, are there any compliance requirements that you must fulfill now or in the future? That could be vertical compliance things if you're working in pharmaceutical or clean water handling. There are compliance requirements. If you have certain customers that has some compliance requirements on the security part. That's important to take that into account. A little bit summary in the end. I'm talking here, I was promising to get back to you on a little bit about the vision. Why is it so important to actually build for scale? And make a little example here. Let's say you build a use case and you defined a pump, you have a pump, and the use case data is just a subset of the pump. So you take the use case data, perhaps 50 tags or 25 tags, publish them to the UNS, and the app is consuming that. Fine, the app is a success, and you want to scale this. And you add pump 2 to pump X, and you define this small amount of data from each pump to the UNS. This will take time to scale because it will require interaction to the local OT teams. But then you realize that you have a use case 2 that needs a little bit more data. And that means that the scaling of this app would probably take not as long as the scaling here, but similar. It will require interaction with the local OT team on each and every site for each and every pump to get that data in. So I would argue that when you do your use case 1, it's on pumps. Fine, let us at least send over the complete data set for the pumps when you do it, because the overhead of sending all the data or just sending the small subset of data, the manpower to define the model, that's very little when you are there already, because normally it's script based anyway. So then you can just send all the data with the pumps. And this means that the use case 2 app would probably be much faster to develop, much more secure to develop, because you have data. And the scalability will be there. So when you design your new use case app, as soon as you have a success with that app, it's automatically available for all the pumps. And also, since you have a full view of all the pumps and you handle them in the same way, you can adopt changes much faster. And if someone adds another 100 pumps, you don't need to do manual work in the cloud or in the app layer. because they are zero configuration. They are built towards the model. So this means that they are self-configured, and that's the power of scale, so that you don't use that much manpower to scale. That's the success of any software business you see today. That's the ability to scale without increasing the amount of manpower in a linear way. So the summary here: learn basic cloud terminology and function so that you as an OT person can take that. And the same with the other way around. The IT people needs to learn a little bit about the OT. Understand the use case, because use data have higher quality. So if you're using the data, that's good. If you create a data ops solution architecture, like I said, contextualize and normalize data on the edge, and let OT build and manage the data flows. Because if they exchange a temperature sensor, they change that in the data ops gateway. This means higher data quality in the cloud, and it scales much faster. Of course, investigate UNS for enterprise scaling. So if you want to build on that, that is some technology or a solution type that you need to investigate. And of course, do your security risk assessment. So that's the summary. And I would like to say thank you, but big thank you for everyone to putting in the time.